All right, welcome back, Dr. Brown et al., whoever chooses to watch this in the future. So now what we're getting at here, we started with a list of primes, and we wanted to make a polynomial that when evaluated at consecutive integers gave consecutive primes, and we derived a formula. You know, it was a pretty complex formula, but we derived a formula nonetheless to find a polynomial that would pass through an arbitrary number, any number you want. I can't say infinite number, but an arbitrary number of primes. Doesn't matter how big of a list of primes, I can find a polynomial that passes through it, and if you understood the previous videos, so can you. All right, so now we're faced with a different problem. Now up here on the screen I've got 3 points. Maybe I should have put 4 for more clarity. You know what, let's put a fourth one in. I don't know, what's your favorite number? Let's put in 1, 6. That seems pretty good. All right, let's put in 1, 6. And let's kind of go through the same process. I've got to have my let's not call it big P of x anymore. I don't know. Let's just call it oh, I don't know, n of x, like this. Now this n of x is going to be a polynomial that passes through the 4 points that I've listed above. Now, because there are 4 points, I'm going to need 4 summand polynomials. Okay? And we can easily construct these summand polynomials as we have in the past. Okay? So the first summand polynomial, which I'll call f sub 1 of x. Now, I need it to have zeros at 8, 3, negative 3, and at 10 and at 1. So I've got to put x minus 1, x plus 3 for the negative 3, right? And x minus 10. Those are the zeros of my first polynomial. It doesn't have zeros at 8 because I want it to actually have a value at 8. I'm going to have to divide by 8 minus 1, 8 plus 3, and 8 minus 10. All right, so far, if you've been following along, let's see, the numerator right now is the blue chunk that I've been following. This is the blue chunk that gives it zeros, and the green chunk makes sure that the blue and green chunk together evaluate to 1 when evaluated at, in this case, 8. Now, all we have to do is multiply by the y value of our desired point. So the y value associated with 8 is going to be 6. Okay, that was like super easy. I mean, of course, this isn't going to be a very nice looking polynomial if you distribute and you know, get this in standard form. It's going to be pretty horrific, actually. And then imagine adding it to 4 other summand polynomials. You know, it's going to be pretty horrific. So, I mean, I'm not going to do that by hand, but your calculator can or a computer can, and I don't really know why one would want to do that. So, of course, just for clarity's sake, let's make another one. So I'm going to have, here I'm going to have negative 3 minus, well, no, excuse me, I'm going to have x minus 8 on the top to put a 0 at 8. I'm going to have x minus 10. I'm going to have x minus 1. I think I put these top ones out of order, but that's okay. Doesn't matter. On the bottom, I'm going to have negative 3 minus 8, negative 3 minus 10, negative 3 minus 1, multiplied by the y value associated with negative 3 is 4. Okay? In a similar manner, you could construct the f sub 3 of x, the third summand polynomial, and you could construct f sub 4 of x. They would have the design. I'm not going to go through these rote calculations, I think, because I think you've got the picture of how to construct these polynomials. It's actually fairly simple once you think about it. So now I'm going to jump straight to the closed form, the most compact form. We'll call it compact. So here's what I do. You have your data set, any number of points. Of course, you would never want to do this by hand. So you take your data set. You need to get rid of any vertically stacked data. So you could make some code or to have a vertical data, I don't know, averager. That's what I'm calling it. Or you could, just throw out a couple of vertical datas. That way it actually can be a function, right? And now what I'm going to do is I'm going to sort it. Honestly, it works without sorting, but I'm just going to put it through a sorter that sorts based on x values from least to greatest. But the y's stick with the x's, of course, because I can't change my points around. The y's have to stick with the x's, but the x's are sorted from least to greatest. All right, not too bad so far. And now I need one more thing. I'm going to label the smallest x as x sub 1, and then they'll increase up to x sub n. So they're labeled in order, starting with x sub 1, going to x sub n. Not too bad. And their associated y values, of course, are y sub 1 up to y sub n. But those are not in increasing order, at least not necessarily. Probably not. All right. Not so bad, not so bad. All right. Now the compact formula for this is going to look almost exactly like this one. So let's start with n data points, index of k on our summation, up from k equals 1 up to n. Now in here, I'm going to have f sub k of x, which is my summand polynomial, right? Okay, now I just have to define what f sub k of x is. And by definition, f sub k of x is going to have zeros at all integer, well, excuse me, this time they're not integers, they're at all x values that aren't the index. Not all x values, but just all the x values that are part of our data set. So not all x values. It doesn't make sense to have a polynomial that has zeros everywhere. But it's going to have x values at every x value that we have in our set except for the kth x value. I hope I said that as clearly as was needed for you to understand. So f sub k of x is going to have the form x minus x sub 1 times x minus x sub 2 and x times x, x minus x sub 3 and times and so on up until x minus x sub k minus 1. And then we're going to skip, like we did before, we're going to skip the kth x. So here I'm going to have x minus x sub k plus 1. All right. And we're going to keep on going until we get to x minus n minus 1 and x minus n. Perfect. All right. Those terms ensure that there are zeros at every single x value in the set except for x sub k, which is what I was going for. Now that's if you guys have been following along, that's the blue chunk. Now I need the green chunk. This isn't too hard. The green chunk is going to be, let's see, what does it have to be? It's going to be x sub k minus x sub 1, x sub k minus x sub 2, so on and so forth until x minus x sub k minus, x sub k minus x sub k minus 1, x sub k minus x sub k plus 1. So we skipped the xk minus xk term, which is good. All the way up to x sub k minus n minus 1. Excuse me. Up here, I made a mistake. This should be x sub n minus 1, shouldn't it? I think so. And this one should be x sub n. Yeah. Sorry for that little mistake there. All right. And done. Done with the green chunk. Okay, holy moly. Holy moly. Not quite done. We only need one more thing. We have our blue chunk and green chunk, and together they have zeros everywhere Not everywhere, but at all x values that are in the data set, except for x sub k. And when evaluated at x sub k, the blue chunk and green chunk together equal 1. So all I have to do now is multiply by my desired y value, which is y sub k, which is, you know, a nice anticlimactic climax for those of you who like climaxes. Not too bad. Let's write f sub k of x in a product form, summation big pi. Is that what they call it? They call this one big sigma. So I wonder if they call this sigma notation. Do they call this pi notation? That sounds kind of weird. Anyway, so let's see. We have f sub k of x is going to be equal to the product from I equals 1 up to k minus 1 of x minus x sub I times the product of I equals, the product from I equals k plus 1, so we're skipping the kth term, the x minus x sub k term, and we'll go up to n, and then we'll have x minus x sub I again. We're not done yet, but I wanted to just point something out that I forgot to point out earlier. This x right here is a variable, because we're making a polynomial. It's a variable. We don't know what that is. Anything that has a subscript, an x with a subscript, is a known value. Or in this case, it's an index. Or in this case, you know, we've got the index on there. So, I mean, I haven't explicitly stated what it is. I mean, I don't even have a data set. But it is a known value. Anyway, so let me get rid of those yellow marks. I don't like those yellow marks very much. All right, so let's see. Let's continue. F sub k. So I've got my blue chunk, right? This is my blue chunk. And now I need my green chunk. All right. So let's go I equals 1 up to k minus 1. And now I need 1 over x sub k, which is a known value, minus x sub I. And then I'm going to multiply it also by the product from I is equal to k plus 1 up to n of 1 over x sub k minus x sub, let's see, I. Yep. All right. So that's what? My green chunk? Yeah, I think it's my green chunk. There we go. So the blue chunk and the green chunk together, when evaluated at x sub k, is going to be equal to 1. So all I need to do now is I need to multiply by y sub k. And to be honest, this still looks pretty horrible. I mean, honestly, it took more horizontal room than what I wrote before, but you know, we mathematicians, we like to scare people with our symbols. So we're nearly done here. So all I want to do here, so I've given you my big sigma notation, and now I've defined what f sub k of x is. I could stop right here, but the next step is going to be really fun. We're going to write it all out. Okay. Big sigma of, so we start, sorry, I should specify what we start with. We started with n points in a data set. And I've already vertically averaged them, and I've already sorted them. You don't actually need to sort them. All right, this is what it's going to look like. Big sigma. The sum from k equals 1 to n of biggest parentheses you ever drawn in your entire life. Okay. Now, on the inside, I'm going to put f sub k of x, which is blue chunk, green chunk, y sub k. So here, big product from I equals 1 to k minus 1 of x, which is a variable, minus x sub I. Now I only go up to k minus 1, so I can skip the kth term. So I start with the next one, I equals k plus 1 up to n of x minus x sub I. All right, so that's my green chunk. Now, excuse me, that's my blue chunk. Now I'm going to do the green chunk. I equals 1 up to k minus 1 of 1 over x sub k, which is the known value, minus x sub I. Is that the same as I had above? Yeah, it's the same. Okay. And now we're going to multiply it by another product, k plus 1, because I'm skipping the kth term, up to n of 1 over x sub k minus x sub I. All right, nearly almost done, nearly almost done. Now I just got to multiply by y sub k. Maybe I should have put another set of parentheses in here, right there, right here. Now I've got to multiply by y sub k. All right, and now I need the last closing parentheses. Holy moly! Holy moly, Dr. Brown. This is what I did with my free time. I mean, you just told me to find a polynomial that gives me primes, and instead of doing that, this is what I did. Which I gotta have somebody to brag to, because I bragged to Scout, and I don't know if he got it, but that's okay. So I don't know. I don't really know why I showed you this other than to brag. So maybe I shouldn't get too inflated. Maybe I shouldn't even have told you this, but this right here, this algorithm at the beginning, this algorithm plus this function, well, it is a function. This will give you a polynomial that passes through every single point in your modified data set. And I do claim it's a function. Let's see. Draw. Okay. Because this function maps is defined, maps, how do I say it? Let's see, I'll just say it maps A to B, where B is an element of any polynomial, is an element of any possible polynomial. So I have no idea how big this polynomial is going to be. I think it's going to be of degree, let's see, I think it's going to be of degree n minus 1, where n is the number of points in your data set. I think it could be less depending on the data set, but it's still an element of this. And then A is going to get a little more complicated. A is going to be an element of any possible sets of in 2D. So it's going to be, I don't really know how to express this. So it's going to be an element of a set, how do I express this? A is an element of a set of points with cardinality, anything with cardinality n. So it's going to be an element of the set of sets with cardinality n. The set of sets, how about I just write it? Sets of ordered pairs of real numbers, with cardinality n. And it maps any set within this set. I don't know what I should call that set. Maybe I should just call it, S2. So A is an element of S2. A is a set element of S2. So it maps an element from the set S2 onto, that was weird, onto a polynomial of degree n minus 1. And I might have messed up this n minus 1 part. I didn't think about that one too hard. So this right here is a function that maps a particular set onto a polynomial. That polynomial will pass through all the points in the original set. So this is pretty funky stuff. And that's all I have for you. I wanted to show you this online. I derived this all by myself. Well, of course, I mean, I was taught, in high school and college a bunch of math, so it's not like I did it all by myself and I'm claiming responsibility for that. I mean, I had a bunch of nice teachers. But after I derived this all by myself, I'm like, this is so cool that I can't possibly have been the first person to derive this. I mean, this was pretty simple and straightforward and brute forced, so somebody did this already. So I looked this up. I honestly don't remember how I found this online after I derived it, but It turns out that it's called a Newton polynomial, which its inventor was Isaac Newton. So that just inflates my ego a little bit more, that I invented something that Isaac Newton also invented. And he did it in kind of the same way I did. He created the sum of summand polynomials, and then he defined the summand polynomials in the same way I have. Well, I mean, Wikipedia explains it in the same way I have it. I wonder if he had the same notation. Probably not. So what is this good for? Let me draw a picture about what this is good for. Let's see, where's my OneNote? All right, so what is this good for? Let's see, draw grid. There's my grid. All right, so if I have any number of points, you already know this, if I have any number of points in 2D, passing a polynomial through these is not going to be super great, right? I mean, give me a break. It might look like this. It sucks. I mean, it's not good for modeling in general. However, if you take for example, a nice data set, a very tight data set, high correlation you might call it, then it is good for modeling. So let's see. Let's see here. Here's another grid. All right, so here's my other grid, and now I'm going to give you a different data set that's like this. If they're very tight and follow a tight curve, kind of like the primes do, then it is good for modeling, because then this polynomial will pass very through every single point, right? It's going to pass through every single point, and when it's closely mapped to a tight curve like this one, then it will match it very well, and it's excellent in these cases for interpolating data. It's almost as best as you can get. It's excellent for interpolating data, especially when you can't make a very good regression because you don't know what kind of model this should be. It doesn't look logistic. It doesn't quite look exponential. It looks like some weird function that's been composed a bunch of times with a bunch of other functions. But you can just make a polynomial that interpolates very well the data. And the reason it interpolates well the data is because we're not going to get something that looks like this. And the reason we're not going to get something that looks like this is because each of the summand polynomials is going to look like this. It's going to be really tight to the x-axis except for up here. And then it's going to go back down to the x-axis. So it's going to actually model this very well. It's going to stick right close to what you think the trail of the data might be. So this is why Wikipedia calls it the Newton's interpolation polynomial. Very good at interpolation, pretty bad at extrapolation, because up here you expect it to keep going up and who knows, it might go down. So it's bad at extrapolation, but extremely good at interpolation. So interesting. There you go. That's all I have for you. Here's the climax right there. Boom. See you later, Dr. Brown.